So, let us continue the discussion. Now, we have already seen the overview of the basic jet propulsion or aircraft engine, their different operation and all this, and how one can very simplistic way can calculate the thrust. Now, we will start or continue our discussion on the some of the basic understanding of fluid mechanics, and then followed by some basic laws of thermodynamics and some of the compressible flows, because these are going to be important later on when we move to the thermodynamical analysis of the jet engine. So, let us start with that. So, with the basic discussion on the, now when you talk about basic fluid, so what you have already looked at that the thrust is developed by importing the momentum on the working fluid. So, fluid mechanics becomes important, and then in propulsion, so that we consider the working fluid to be in continuum. So, the continuum hypothesis would be valid, and there are 4 basic conservation laws which one has to satisfy. Obviously, there would be mass conservation. Okay. These are basic governing laws. Then Newton's second law of motion or momentum equation, Newton's second law of motion, or one can think about momentum equation. Third, this is energy equation or conservation of energy, which comes from thermodynamics, and then we also need second law of thermodynamics. Okay. And now, one can write these different form of equations and different ways. Now, apart from this, we need one more conservation laws, which is the conservation of angular momentum. So, this would be required in addition basic 4 conservation laws, while we will be talking about the turbo machinery part, like for turbine or compressor. Okay. Now, there are 2 thermodynamical cycle where things can operate. One is the, if you look at that, one is the Brayton cycle, another is the Humphrey cycle. So, first let us see the Brayton cycle. So, if I draw the PV diagram for a Brayton cycle, so this could be 1, 2, 2, then it goes to 3, comes to 4. So, this can 2, 3, 1, 4, there could be 5, 6. So, P2 is P5 here, this is P3, P1, P4, and equals to P6. So, this is the volume V2, V3. Now, this is a Brayton cycle where you have constant pressure combustion. Okay. Now, other one, if I draw the TS diagram, so 1 to 2, then it goes to 3, then it comes to 4, 1, 2, 3, 4, 5, 6. So, now this guy is 1, 2, 5, 6, 1. So, that is in the PV diagram. Now, when we talk about the Humphrey cycle, it is 1, 2, 3, 4, 1. So, this portion is the Humphrey cycle in PV diagram. So, this is the TS diagram. So, you have T3 equals to T5, this is 1, 2. So, you have S1 equals to S2, S3 equals to S4. Now, in Brayton cycle, one can write the efficiency is 1 minus T1 by T2, this is again ideal, and Humphrey cycle is constant volume combustion process. So, there one can derive the thermal efficiency like 1 minus gamma T1 by T2, T3 by T2, 1 by gamma minus 1, T3 by T2 minus 1, where gamma is Cp by Cv. So, you can see the cycle efficiency in Humphrey cycle depends on also T1 by T2 and the temperature T3 by T3 by T2 in effect of pressure. So, if you plot a curve for these two, for just to compare, this is the combustor exit temperature in Kelvin. So, let us say it starts with somewhere 1600 to goes to, and this is the efficiency, let us say this is 0.8, and the cycle efficiencies are different. Now, one goes like this, this is your Humphrey cycle, which is 0.78, and somewhere Brayton cycle efficiency would be around 0.64, something like that. So, there is a difference, but obviously there is another issue which is the process of combustion. One is constant volume, one is constant pressure. So, there is a big difference between these two. So, this is a basic thermodynamical cycle that one. Now, some definitions. One definition could be system. This is a quantity of matter in space which is analyzed during a problem. Then you have surroundings, that means this is everything external to the system. Then you have system boundary. So, the separation present between system and surroundings, this is, so there could be solid boundary, real solid boundary, or there could be imaginary boundary. So, just like if you have a so system like this is all surroundings and this is your system boundary. Now, the system boundary can be classified into two different categories. One is the fixed boundary, which is called the control mass system, or it could be moving boundary, which is called the control volume system. Now, which one boundary is to choose, that depends on the problem to be analyzed, or another one. So, any not the system boundary, rather we put the classification for a particular system, or the third one could be isolated system. So, one is closed system. So, let us say, okay, let us put it the, So, we will now define based on the system. There could be closed system, which is control mass system. There could be open system, which is control volume system. Then there could be isolated system. Okay. Now, when you talk about system, what is system? System is a collection of matter of fixed identity. It may change shape, position and thermal condition, but always have the same matter and hence the mass. So, system has its system of fixed mass with fixed identity. Then the type of system is usually referred to as, so when the system has fixed mass with fixed identity, this is called the closed system. And if there is a closed system or control mass system, there is no mass transfer across the system boundary. Okay. But there is no mass transfer across the system boundary which takes place, but the energy transfer can take place across the system boundary. Then there is control. So, if this is a control mass system, so one can have energy in, energy out, this is the boundary and this is the surroundings. Now, when you talk about the control volume system, then this is the boundary. So, you can mass in and mass out, you could have energy in and energy out. Okay. So, the example of such control volume is a definite volume designated in space and matter can flow in and out of it. Thus, this is the boundary of this volume is also called control surface. Since fluid consists of infinite CML packets of small system, control volume approach is more appropriate. Like you can think about the example of heat exchanger, pump, and so certain things it has a fixed volume, that is one thing. So, this is referred as open system or control volume system, and we said mass transfer can take place, energy transfer also can take place across the system boundary. So, this is more appropriate. So, this one can see this control volume can be as a fixed region across which mass and energy transfer are studied. So, boundary of the control volume where this mass energy transfer takes place is called the control surface. Mass of the control volume or the open system may or may not be fixed. So, mass of CV system may or may not be fixed, that is another important thing. When the net influx of the mass across the control surface equals to the 0 of the mass of the system is fixed or vice versa. So, the identity of the mass in a control volume always changes, like the case of control mass system, and most of the, as I said, engineering devices in general represent an open system or control system, control volume system. Now, other one is the isolated system. So, the isolated system, it is a system of fixed mass with same identity and fixed energy. So, this is a fixed mass with same identity and fixed energy. So, there is no interaction of mass and energy takes place between the system and the surroundings, between the system and surroundings. In more informal words, an isolated system like a closed shop amidst a busy market. Okay. Now, these are the different definitions. So, now we will go to one important thing is the Reynolds transport theorem or called RTT. So, a study of fluid in Eulerian approach always requires some mathematical modeling of the control volume, either in differential form or integral form. So, the statements of principal conservation of mass, momentum, energy with reference to a control volume is quite necessary. So, this can be derived by invoking. So, what it states that the RTT says the time rate of increase of property in within a control mass system is equal to the time rate of increase of property n within control volume plus the net rate of efflux of the property n across the control surface. So, this is the statement it says. So, if we write that if the, so once you derive that, this will looks like dN by dt across a control mass system, which is del del T of control volume eta rho dV plus control surface eta rho v dot dA. So, this is velocity, this is volume. So, n is the flow property which is transported, eta is the intensive value of flow property, and so which is n by per mass, and then this is the first term, this is second term, this is third term. So, the first term is the rate of change of any arbitrary extensive property of the system, property of the system. Term 2, which is the time rate change of arbitrary extensive property n within control volume. So, where rho dV is an element of mass contained in the CV, and the and eta rho dV, which is eta rho dV is the total amount of extensive property in contained within CV. Third term, which is the net rate of flux, of extensive property N out through the control surface. Here rho V dot dA is the rate of mass flux through area element dA per unit time, and eta rho V dot dA is the rate of flux of extensive property through N through area dA. Now, once you see that, so this gets you, so when N is m, then eta is 1, which leads to the conservation of mass or continuity equation. If n is p, then eta is v bar, this is conservation of momentum equation. If n is h, eta equals to r cos v, this is conservation of angular momentum. If n is e, eta equals to small e, this is conservation of energy equation. If n is s, eta equals to small s, conservation of entropy. So, you can see for different n and eta, you can derive all the conservation laws that we have talked at the beginning. That means, this RTT is quite handy to define this kind of governing laws. For example, so we can write, for example, let us say the mass conservation equation. We write dm by, this is our RTT, CMS, which is del del T of control volume rho dV plus control surface rho V dot dA, which is 0, because the total mass in a control mass system is constant. So, this is 0. So, this is our mass conservation equation. Now, using the Gauss divergence theorem, one can write control surface rho V dot dA would be written as control volume delta dot rho V dV, then this will become del del T control volume rho dV, control volume del dot rho V, now dV which is 0. So, you can write, so if you take this, then one can write del del T rho plus delta dot rho V dV equals to 0. This holds good for any volume and it vanishes these things. So, what we can write, del rho by del T plus delta dot rho V equals to 0. Okay. So, this is what one can write in terms of vector notation, and if somebody writes in indicial rotation, this would be del rho by del T del del x I by rho u I equals to 0. So, this is in indicial notation. So, one can write in initial notation also. Now, this is an equation of mass conservation or continuity equation which is valid for any flows, like this is valid for both compressible and incompressible. Now, for incompressible, we can derive the special situation for incompressible flow, but do not make this mistake which is very common, is that okay, incompressible flow density does not change. That is not the way it is derived. Now, you can see what, so density does not vary too much, but so people usually make this mistake straight away. Okay, for incompressible flow, you just say, you write down this and you say this goes 0, then density constant. So, this becomes del dot V equals to 0. So, this thing is not correct. So, this is not correct way of doing or derive that equation. Rather, one has to do for incompressible limit that expand that the second term, which will get you del rho del dot V plus V dot del rho, which is 0. Now, this term would give me d rho by dt plus rho del dot V. So, this term and this term collectively, so this is called the total derivative or material derivative. For incompressible limit, this goes to 0. So, this becomes rho del dot V 0, since rho is not equals to 0, this is what you get for the incompressible flow. So, this is the right way of doing it, these things. So, we will stop here and we will continue the discussion for the other conservation laws and how we can derive in the next lecture.